acids have quite a long history with the Deep South, so there's been quite a long evolution of sea ice research, of oceans NZESM modelling research, and also of the core NZESM modelling work itself as well. So we'll hear from those three about kind of where the, I guess, some of the researchers got to and what some of the really salient parts of that are in terms of the commission work as well. We've only got an hour, so I think it's 10 minutes for the talks and 5 minutes for questions afterwards, which is pretty tight, but I don't have any kind of bell or anything. I'll just knock if we're going too far over, wave my hands about a little bit. But yeah, so do prepare questions. Also, you know, you've got three researchers who are really, you know, you can ask questions about sea ice, about ocean modelling, about global modelling to these three as well, that if you've got questions that sit, that might not be within the presentation as well. I'm just offering their services for some questions there as well. So we're going to start with Andrew and then Eric and then Olaf. Andrew, I'll pass over to you to share your screen and speak from Otago University.
That's great. Hopefully that shows up okay for everyone. Yeah, so I'm Andrew Pauling. I'm a research fellow at the University of Otago, and I've been working as part of the Deep South Challenge modelling effort on modelling Antarctic sea ice. I've been here since last year, but this is, as Kate mentioned, been a part of our research for sort of the last 9 years or so, led by Inga Smith here at Otago and involving all the people you see listed here. So just some background. So what is sea ice? Sea ice is frozen seawater at the ocean surface. It's formed from salt water, so it has salt in it. It's typically about 1 to 2 meters thick. And as shown in the image on the right here, the annual cycle of Antarctic sea ice, it varies between about 2 and 20 million square kilometers of ocean that it covers annually, so between the summer and winter every year. So that's a change of more than 60 times the size of New Zealand. So it's one of the biggest seasonal changes on Earth. If you take the annual average and look at that over the time that we've had satellites, here on the right, I'm showing Arctic and Antarctic sea ice in the blue and orange respectively over the satellite era, so since 1979. And as has been pretty well publicized, Arctic sea ice has declined steadily. Antarctic sea ice has been more of a puzzle. Between 1979 and 2015, it actually increased slightly. And then since then, it's declined pretty sharply. And models don't reproduce Antarctic sea ice very well, so that's been a focus of our research. So here I'm showing the kind of a video of the annual cycle of Antarctic sea ice. This is from a model, but this looks very similar to observations. And you can see how big of an area of ocean that covers in the winter, and then how much it shrinks away again every summer. Oops. So the other important aspect of our research has been the Antarctic ice sheet. And so this is freshwater ice on top of the land in Antarctica. It's formed by compacting snow over hundreds of thousands of years. It's several kilometers thick in the middle, so much, much thicker than sea ice. And so Antarctica can lose mass by icebergs breaking off, what we call calving, or melting of the floating extension of the ice sheet over the ocean by the ocean water underneath. So we call that basal melting. The problem that has been the focus of my research and a lot of the group's research over the last few years is that climate models don't represent Antarctica very realistically at all. So in contrast to the cartoon representation here, this is what models say Antarctica looks like. So they don't have real ice sheets. They treat the ice as land with snow on top. And so in the models, Antarctica can't gain or lose mass. It's forced to just stay the same the whole time. In the real world, it's losing mass. And so there's this missing source of fresh water from the melting ice to the Southern Ocean in the models. And we're interested in the impact of that fresh water on sea ice and climate in general. So why does this matter? So adding fresh water cools the ocean surface. I won't get into the details of how that works here, but basically it blocks warmer water from deeper in the ocean from reaching the surface, and so you have a net cooling effect. This results in more sea ice because the ocean surface is cooler, and this effect spreads far beyond Antarctica. So on the right here are from a study I was involved in a couple of years ago, changes in the trend in surface air temperature, sea surface temperature, when you add this fresh water, both over the historical period on the top, so the satellite era basically, and on the bottom into the future out to 2100. And so you can see that adding this fresh water relative to a control without it cools the Southern Ocean and extending well up to around New Zealand. So the fact that this is missing from models is we're missing this cooling response in our projections of temperature for New Zealand. So I'm going to walk through kind of the major projects that have this group has done over the course of the Deep South Challenge. So one of the first was a new parameterization for what we call grease ice. So this is less related to what I've just talked about, but still important work that we've done. So grease ice is the very thin layer of ice that just first forms when sea ice starts to form in the winter. And a team led by Shona Mackey, who is a previous research fellow in this group, implemented a new parameterization for grease ice in the sea ice model that's used by the New Zealand Earth System model. They tested it in what we call HADGEM3, which is basically the physical core of NCDSM, and that's the model we'll use for all of this work. It resulted in thicker sea ice in the Arctic, and there were some local differences in the Antarctic, but little overall impact to total sea ice volume. The next project that was also led by Shona a few years ago was starting to look at this impact of Antarctic meltwater in HADGEM3. And so she tested the impact of ice shelf and iceberg melt under pre-industrial control, so a fixed, unchanging pre-industrial climate, and then also in a scenario where CO2 increased.
I think we've lost Andrew.
And the increasing meltwater input was enough to offset the sea ice decline in that 1% CO2 scenario. So this can have a really big impact on the climate response in these models. It also enhanced the projected decline in Antarctic bottom water formation, which is really important for the global ocean circulation. So this has really global impacts, this freshwater. Following that project, Max Thomas was another research fellow in the group up until the end of 2022. So he investigated the response of continental shelf waters in the ocean around Antarctica in the same model. He found that subsurface waters warm in response to the fixed meltwater input. So the surface cools when you add this meltwater, but because it's blocking the warm water from coming up from depth, you get warming at depth in the ocean. And he found that happened in a future warming scenario with the addition of this meltwater. So that has implications for the feedbacks on the melting of the ice shelves if the deeper ocean is getting warmer. This additional meltwater resulted in cooling in some regions and warming in others. And the response depended on the exact continental shelf properties, climate, and the distribution of the freshwater input. So a lot of detailed work in that project. And then finally has been my work since the start of last year. So historically, the impacts of Antarctic meltwater on Antarctic sea ice have varied a lot depending on the model used to study it. And so our team now is participating in a new international multi-model intercomparison with a standardized meltwater input and the Southern Ocean freshwater impact from an input from Antarctica initiative, or SOFIA. And this has been a modeling effort so far with about 10 different climate models from around the world participating, and we've been running the HADGEM, which is the base of the New Zealand Earth System model, to contribute to this. I'll quickly go over a couple of results. So this is the Antarctic sea ice area response in the first of the simulations from this project. So this is under pre-industrial control forcing, so no global warming in the simulation, just the meltwater. And so this increases Antarctic sea ice area from the beginning of the simulations. And there's a really big spread depending on the model used in the size of the response, up to a factor of sort of 3 to 4 in some of these models, depending on which model. So it really matters which model you use to do this. And it's important to have these model intercomparisons to know what the uncertainty in this response is. Looking at sea surface temperature, so here are the 10 models that we have participating, and this is the sea surface temperature response to this meltwater. So there's cooling across the Southern Ocean in all the models, as we've seen. This extends up to New Zealand, as I said earlier, and it has a potential to reduce projections of warming when included in the models. So zooming in on New Zealand, you can see there's quite a big spread depending on which model you use and the amount of cooling. Averaged over this box around New Zealand, it's between 1/4 and 0.65 of a degree relative to not including it. So it highlights the importance of these intercomparisons. Please note this is an idealized experiment and doesn't correspond to a future projection. So finally, meltwater from Antarctic ice sheet is an important missing process. It has important implications for Antarctica and New Zealand. These intercomparison projects are critical for quantifying the uncertainty. This has been proposed to be included in CMIP7, and a few of us from our team are involved in those discussions. And so we have future scenarios, including Antarctic meltwater, being run now, and those results will be coming out soon. Thanks.
Awesome, thanks, Andrew. It's a real great kind of walk through the different phases of the research across the Deep South years. I have questions I can ask, but I'm not the one who needs to ask the question. So just want to open up the floor for anybody who might have questions for Andrew.
Andrew, do you anticipate the advances, that means the freshwater flux, to be part of, let's say, the next UK Met Office model contributed to CMIP7?
So I'm a part of an effort at the moment led by Gavin Schmidt at NASA to try and get this freshwater included as a standard forcing in CMIP7, especially in the historical simulations, because we have some pretty good evidence now that including it does make a difference. I don't know if we'll get that in time for CMIP7. I also know for the UK ESM in particular, they do have a coupled ice sheet, which removes the need for manually adding this fresh water if you have an ice sheet that can feed back with the ocean. So that could be also an option in the future. I'm not sure which one will happen in CMIP7, but yeah, both are on the table.
Saw your message come up, Karen, so we will have some time at the end as well. So yeah, if you are still digesting, we'll hopefully have a little bit of time at the end to ask questions as well. I wondered, Andrew, I know the team is working on, and you did reference it earlier, the implications, I guess, for New Zealand climate and the fact that meltwater effectively cools the atmospheric warming that we might see. I know that the team's doing a bit of work this year to look at implications for New Zealand climate as kind of the next step that might come out a bit later on after the Deep South. But without kind of preempting you too much, do you have a sense of the questions you're asking and what types of things might come out of that work? I'm just thinking from implications for New Zealand, risk assessment style lens, what you might see coming out of that follow-up work that you're doing.
Yeah, so I think for sure we'll have a good idea of the change in temperature relative to the existing projections that we would expect if you include this effect. And given that it's in this model intercomparison, we should be able to also give a good range of values, so a kind of high and low estimate. There's some evidence that adding this meltwater also has effects on the winds for New Zealand. So it strengthens the circumpolar westerlies a little bit, which will have implications for New Zealand weather, but we haven't yet been able to quantify that. So that will be coming soon once all of these models have run this next set of simulations. So yeah, impacts on New Zealand weather from kind of both of those factors. And yeah, we're interested to see what else we can find here.
Fantastic. We are perfectly on time. So thank you, Andrew. That was really great. I might hand over now to Eric. So Phil, I think you're going to drive.
Yeah, Andrew, could you just stop sharing your screen, please, and I'll bring up Eric's.
Yeah.